That's great. You're very welcome, everyone, to this webinar on digital technologies and land use net zero. My name is Jim Harkin with Ulster University, and I'm the lead for the topic advisory group on digital opportunities within the Land Use Net Zero Hub. And I just want to have a brief introduction today of before our three key speakers come in on different case studies. The focus today is on trying to make people aware of some of the technologies that are available there that can help us and gather information and maybe hopefully move on to inform policy. I want to just mention just about the Land Use Net Zero Hub. Many of you on the webinar will be aware of the hub and its work. Just to mention, it's launched in 2024 in January. Unofficially kicked off November 2023. The funding came in, the project started, but the official launch with the hub consortium was just in the beginning of 2024. The hub's really focused on trying to, I suppose, establish support the transformation of land use, I suppose, necessary to achieve the UK's greenhouse gas emissions targets by 2050. And the hub's not focused on trying to do new research, but very much kind of synthesize what's been done at the moment across different research organizations and universities, and try and collate that and help inform policy. And within that, there's a number of topic advisory groups, and digital opportunities is one of them. And the focus of that TAG group is to try and look at digital technologies broadly. So that's everything from what you might expect from AI to data, right through to simply dashboards and how you can display information. And the topic advisory group for digital opportunities is really looking at how technology can maybe assist us in gathering evidence, how it can assist us in terms of making more effective change. So looking at new disruptive technologies, what's out there at the moment. Many of you are aware of Gen AI. How can we use that to support, gather information, and inform or change policy? So digital opportunities really has a broad remit and how we can support the hub. And one of the activities is dissemination here today, looking at trying to get across what technologies are being used and how they're used to help affect, I suppose, decisions and land use change. So just about our background, I just want to, I suppose, move on to the interesting part here, the focus. Today, we've got three case studies being presented on the areas of IoT and sensors, digital twinning, and geospatial technologies for monitoring land use change. So these case studies, these topics are derived from just consultation with different stakeholders to find out initially what is the areas that they'd like to find out more information about, the applications and where they've been used and some of the outcomes. So today, delighted that we have Jonathan Evans, Azman Khan, and Toby Wayne here to present on these different technologies and how they've used them in their areas. And I'm going to just stop sharing for a second here and just allow you to maybe Jonathan, our first speaker, to get his presentation shared. And just to give a bit of background to Jonathan. So Dr. Jonathan Evans is a hydrometeorological instrumentation expert. He specializes in the measurement and science of land, atmosphere, fluxes of water and energy. And his research is in the application and development of novel and cutting-edge observation techniques, especially around cosmic ray neutron sensing techniques for the field scale measurement of soil moisture. And since 2013, he's been a technical lead of the Cosmos UK Soil Moisture Monitoring Network and has led similar work in India, applying root zone soil moisture products and agriculture advisory systems. And Jonathan leads strategic change to implement best practice automated telemetry near real-time field monitoring networks for hydrometeorology and greenhouse gases. So Jonathan comes today with a great experience background in sensing IoT, and very looking forward, Jonathan, to hearing your case study here. So I'll hand it over to you, Jonathan, for your presentation.
That's great. Just checking, Jim, you can see the slides in presentation mode.
Can indeed hear you as well.
Great.
Thanks.
Okay, thank you for the introduction. Yeah, so I'm going to talk about some of our sensor networks in UKCH. Let's move on to. So yeah, I'll be covering, as Jim's just mentioned, the Cosmos UK National Soil Moisture Monitoring Network. A very quick look at some of our UKCH greenhouse gas flux network, which is operated by some of my colleagues, and what myself and a large team of people are now currently working on, which is new infrastructure for floods and droughts research, which is again a new field monitoring and sensing. So the Cosmos UK network started just over 11 years ago now, and it delivers UK-wide soil moisture and weather data using a technique known as cosmic ray neutron sensing. The cosmic ray part is just, it indicates that these are naturally occurring neutrons that we use to probe the soil, and the water content in the soil basically affects how many neutrons we count above the ground. It's quite complex in terms of those processes going on, but it essentially enables us to have a large area field scale soil moisture measurement, and this is the really sort of novel part. Although we've been operating these devices for over 10 years now, when we first deployed them, this was really novel to be able to have a large field scale measurement of soil moisture, and that really bridges the measurement gap in terms of spatial scale between point sensors, which tend to measure less than 1 litre of soil, to up to the satellite scale, which typically may have soil moisture products at 1 kilometre resolution. And yeah, the sort of advent of this new technology has enabled us to deploy a low maintenance, near real-time telemetered network. So we operate these sites under a fairly low maintenance regime with only about 2 site visits per year, and all the data is telemetered back every hour. So why would we want to measure soil moisture? It's something which has become apparent during this project, actually how many applications there are for soil moisture. I mean, obviously we were aware of many, but more have emerged. So there's the fundamental process understanding for hydrological modelling, how water flows in the natural environment, how water's moving through the soil, and then how that recharges groundwater for usually water supply, potable water supply networks, and agriculture. And of course, soil moisture may have a controlling influence on the development of a crop and the ultimate yield of that crop, and the carbon sequestration, therefore, of that crop. And we can use this technology and soil moisture monitoring in general for irrigation scheduling, which I'll talk more about. It's an input to land atmosphere models. The evaporation from the land surface is important control on boundary layer development and the weather systems, and how much evaporation is often dependent on the available soil moisture content, as are the emissions of greenhouse gases from the soil. Microbial activity is controlled by soil moisture. We have a number of climate studies as well, looking at how soil moisture changes in the future and how drought might change in the future. Landslip, hill slope stability is really important. Good examples along railway lines and the risks for the rail network in particular. flood forecasting, weather prediction, and by hydrological outlook. So if we're entering a dry period, how is that progressing? And similarly with periods of saturated wet conditions. So I'm going to talk a little bit more about the instrumentation deployed at a typical Cosmos UK monitoring site. It's a quite sophisticated research grade instrumentation, and we have measurements of the whole, all the normal weather parameters, including what we call 4-component radiation. So that's sort of incoming sunlight and reflected sunlight, as well as long wave energy and incoming, outgoing, and temperature, humidity, air pressure. Many of these things we actually need to process the neutron count data into soil moisture. We have rain gauges at the site, and we also have an array of more traditional point soil moisture sensors that give us information through the depth profile. The cosmic ray soil moisture sensing is primarily sensing the top 10 centimeters of the soil, the water content of the top 10 centimeters of the soil. So it's usually very useful to have deeper measurements as well, and to have information as to how that soil moisture varies with depth. So yeah, just to emphasize again the scale issue, we are using for our point sensors the top left green device here stuck into the soil. It has some metal rings that go into the soil to measure the water content, and as I say, it's measuring a volume less than 1 litre, whereas the white tube here is receiving neutrons from a radius of about 200 meters. That's about a 10 to 12 hectare measurement area. And that's kind of shown in the image on the right hand side, the sort of area we're measuring soil moisture over. So a few of the applications that colleagues and myself have worked on, several studies have compared gridded model outputs such as the Joules land surface model from the UK and Earth observation soil moisture data sets with Cosmos UK data. That's a fairly simple comparison type work which can be done in different ways. And then there's some more sophisticated data assimilation work which I'll talk about. And one of the benefits of these sites is that the site itself has all the relevant model driving data, and we do also have measurements of actual evaporation, which are derived from the land surface energy balance. On the right-hand side, I didn't mention that the sites all have phenology cameras. So we have 5 of these images, pairs of images per site per day, and that gives us a good idea of the local conditions, as well as what crops are growing in the surrounding field, which is important for the interpretation of the data. And we can also use the UKCEH land cover plus crops product to know what cropping there was in any particular season or year. If there's snow on the ground, we can also use the neutron counts to calculate snow water equivalent. So this is a little bit of a dive into a data assimilation application using Joules, and this is work done by Reading University and Liz Cooper here at UKCEH. And there's references there if you want to find out more. But essentially, the orangey line is the prior soil moisture predicted by the Joules model for the location around a Cosmos station. And then after data assimilation procedure, we end up with the blue trace, which is the calibrated soil moisture, much closer to the pink circles, which are the observations from Cosmos UK. And this is done in such a way that the actual pedotransfer function, so the hydrological relationship between soil texture and hydrological properties are optimized, so that makes it more transferable to other sites. So there's a map here of the UK network. We have, I think, currently 47 sites operating for various reasons. Some sites come and go depending on landowners and land management. But we have UK-wide coverage with varying spatial density, and we sample a wide range of climate, land cover, soils, geology, and topography. And where possible, we co-locate with existing research and monitoring, and that's obviously can make the data much more useful, more powerful about co-location. And when we use techniques such as calibration, validation, data assimilation, and machine learning to really use the data in a meaningful way in developing improved gridded products. And ultimately, of course, everyone wants to know everything everywhere, not really just at a Cosmos station. And because of the variability of soils and the geology, particularly in the UK, as well as land cover, if you're not fairly local to a specific observational site, you could have quite different behaviour when you're only, relatively, well, if you're only a few miles away, you could still have quite different soil types, for example. So it's really important we use our UK soil maps to extend this information spatially. So we, and well, ourselves and colleagues have been involved in a number of publications, trying to provide, well, we do provide data sets which are well, can be used for new insights and actionable information. So a recent publication late last year was on future soil moisture drought frequency. So this was an extension of the data assimilation work to calibrate sites using Cosmos UK data, and then use forward climate projections from the high resolution UK CP18 products to run the Jules model forwards in time right up to 2065 and show the increase in drought risk at those sites. So this could be really valuable in planning water resources for agriculture, for example. Do we need to build new reservoirs, how we would manage water, or indeed what sort of crops we would be growing there in the future. And yeah, it's obviously really important that we can show value of the data sets, and these are publicly available data sets, so you're all welcome to download, use the data as much as possible, and that helps us to attract and sustain our National Environment Research Council national capability funding. And then we in turn can use that to have even more innovative and exciting measurements. So here's a kind of end goal, if you like, is a machine learning daily soil moisture map for the UK, which has used many data sources, including Cosmos UK. We're finding this machine learning approach is actually producing really good quality outputs. There's always a challenge with having sufficient data spatially to test the quality of those outputs, but we're pretty pleased with this product, and we're trying to get it set up now so that we have the real-time feeds for precipitation input and others to enable us to run this daily in real time. Yeah, so this is just showing you where you can get data. There's our Cosmos UK website, and since last year, we have an API, so you can use code to pull down data daily and use in your own modeling and analysis. You can download whole data sets from the UKCEH Environmental Informatics Data Centre, and we're now putting our soil moisture data into the International Soil Moisture Network, which again is having really high impact in terms of number of downloads. We've had over 4,500 downloads of data from the ISMN since 2023. So a quick example from India, where we have a smaller scale Cosmos network. And this is really just touching on the demand for irrigation I mean, you can imagine this might be a warming world in the UK, and India might, in some circumstances, represent some of those hotter, drier conditions that we may face in the UK in the future. So a lot of agriculture in India is fed by groundwater irrigation, supplied by groundwater irrigation, and due to overuse of groundwater, there's a huge problem of groundwater depletion, and groundwater can be pumped from many hundreds of meters below the ground, even up to about 1,000 meters. And there are estimates here that groundwater irrigation accounts for 18% of the national electricity consumption in India in 2017. And I think that's, if anything, probably maybe on the low side, or it's increasing all the time. And of course, much of that electricity will be produced from fossil fuels. So that there's a real need to improve water use efficiency in agriculture in India, and having soil moisture information available, as well as other policies to support that, could help to increase water use efficiency. So here's just a simple example of that, where so it's just a simple example where we use soil moisture data from the field and combine it with Earth observation data, and we can also use feedback from the farmer, can input via a mobile phone app what crop is being grown there, and the farmer could be given irrigation advice so that they water when it's necessary, not just when there's power available to turn on a pump. And yeah, so this can both improve the crop outcome and overall water resource sustainability, but also reduce energy consumption and greenhouse gas emissions. Right, moving back to the UK, this is work I used to be involved in. It's now led by colleagues Ross Morrison and Terry Reuter, Chris Evans in UKCEH. They have a number of monitoring sites. We've got a high number now, 48 active sites, mostly on peatland and some agricultural sites, measuring directly the carbon dioxide and, in some cases, methane, nitrous oxide exchange between the land surface. So emissions of greenhouse gas from the natural land surface. And yeah, just a quick slide on how that's done. It's relatively sophisticated in instrumentation, although it's now routinely deployed. And in this cartoon, that there's the air turbulence, the wind blowing over a rough surface, and you have these turbulent eddies, and they carry in the daytime, when you have photosynthesis and transpiration from plants, you have moist air and CO2 depleted air rising, and then drier CO2 rich air coming down. And at the bottom, you see the balance of that net ecosystem exchange in terms of grams of carbon dioxide per meter squared per day. And these measurements, because we're measuring the wind turbulence and very small changes in gas concentrations, they're high resolution instruments sampling at 20 times per second. But this gives direct measurement of those greenhouse gas exchanges. Okay, so the third part is what I'm currently leading, which is a new observatory for floods and droughts research infrastructure. This is to support improve UK floods and droughts resilience ultimately, but we're building essentially a research platform for scientists to come and work in the field and work with field observations. This was this has been through quite a long planning, scoping phase and planning phase, and the full business case was approved by DSER in August last year. So this is actually about £38 million of funding overall, with about 16 million of that going into field observations. So again, we're looking at monitoring the whole hydrological cycle and using really all available tools and methods, including Earth observation. It's focused on the water quantity, but there will be some water quality measurements, stream flow gauging, measuring groundwater. We are doing this in collaboration with the British Geological Survey, University of Bristol and Imperial London. And it'll be really important to build capacity in sensing and in the application of that hydrological data, as well as innovation in sensing. And we're working on the right hand side there, you'll see that we're working in 3 catchments, one in a part of the Thames, the Chess catchment in just north of London in Buckinghamshire, and the Upper Severn in Wales and the Tweed in the Scottish borders. So the kind of new things we're going to be doing, or we're already doing, is using video from either fixed cameras or drones, and in some cases satellites, if we can afford to purchase those acquisitions or get those acquisitions paid for. And if we have live videos, you can see the stream here, you can see ripples on the surface of the water. You can have video monitoring to see how quickly those ripples are moving along, and you can calculate your surface of velocity from that video recording. We're also experimenting with doing this with thermal near infrared cameras that are used for search and rescue, and that often provides quite good thermal identification of thermal features when there are no visible features. So that's looking really promising. And a key point of this work is to be able to measure outer bank flows on the floodplains, which are not commonly recorded properly. So we often don't measure our peak flows, and this is going to be really important for understanding, for example, natural flood management, and whether those interventions are successful. So a really important part of FDRI is the digital work, and this is how most people will interact with FDRI through the use of the data sets, but there will be specific data labs and platforms where we bring all that data together and make it much more usable. So really application ready data sets. And then an exemplar of gold standard sensor data management, and a real opportunity for data commons, providing new research opportunities, and again thinking about making our data ready for machine learning and AI applications. So this is really exciting in having a really well structured a data system where people can work really efficiently and effectively with a whole range of data sets in one place. So this is just an acknowledgement of people that have worked. This is just on the Cosmos UK part of the work I've described. It takes a lot of people to run these networks over extended periods, and so we're very grateful to everyone that contributes. And there's another team that on the greenhouse gas, which I haven't mentioned, and obviously the FDRI team is another huge number of people. Okay, that's my presentation. Very happy to take any questions. Thank you.
Thank you, Jonathan. Some excellent examples there that you shared with us. I'll just open up for questions, and I suppose I just see one question already came on the chat. And if you would like to ask a question, please do raise your hand and we'll come to you. Or if you want to type in your question, please do as well. I just see there's one question come in there in the chat. Jonathan just was asking, is there any capability to scan the root architecture over the top 10 centimeters of soil? So assuming that's your earlier case study.
Yeah, I think that's a really good question, and it's a good reminder to me actually in our FDRI station designs that we're just producing now and just starting to buy equipment. I had do intend really to have some form of root camera system would be great. I think it is really important to know routing depth if you're trying to model soil moisture. That's really valuable.
Okay, great. I just see thanks, Jonathan. I see Ian has his hand raised. Ian, do you want to come in and ask your question? Thanks.
Yeah, no, thanks, Jonathan. Great presentation and great resources you've got there. I guess as a crop scientist, I've got sort of a couple of questions really. Sort of one is really around the way that clearly you're looking at over field scale, and it's what's the level of thinking about the level of heterogeneity and the variability of that heterogeneity from site to site in terms of how we think about how we can make agricultural interventions. The other one, again, thinking about agricultural interventions in relation to the sort of the work you're looking at, sort of, I guess, the sort of water flows and so on, is are you looking at agricultural interventions in that as well, or is that just other forms of intervention?
Yeah, so sorry, could you just repeat that last part again? Water flows?
Yeah, so on the water flows, the last bit you're talking about, so again, the where you're obviously doing a lot of monitoring about water flow, nutrient flow. Are you looking at the effect of agricultural interventions on that?
So I think the short answer is yes. But it will be through a funded science program. So we're building a capital infrastructure for the Natural Environment Research Council and the community to use. There will be funded research programs that people bid into for science projects, and then it would be one of those science projects would probably look more specifically at farm clusters and what's going on in a specific farm cluster and how that's impacting or reducing, whatever it is, sediment runoff or nutrient runoff. So yes, we'd expect to have those projects. We're not, one of the challenges with the floods and droughts research infrastructure is we have to build it for a wide range of science questions and themes. So it's a quite a balancing act to get that right. And then, sorry, the first part of your question was, oh yes, the heterogeneity. Yeah, this is always really a key issue in terms of how we sample the landscape and larger areas. As I say, I think particularly in the UK, we have so much variability in soil types, and you know, even across one field, you'll have quite a bit of variability and maybe compaction of soil in one place and not another, as well as even the topography across that field. So I think we're always looking at how we could sample more spatially, but without sort of incurring huge costs. So this is the challenge, really. I mean, we can certainly do some survey work, and you know, thinking about the sort of drone type activity. I mean, that there are soil moisture radars that can be flown on drones now, so we can do that in a sort of limited way, but that can help identify spatial patterns at certain times. And you know, we also use things like land surface temperatures from satellite to maybe identify areas of different behaviour as well.
That's great.
Yeah,
Thanks, Ian, for that question. I just see maybe time for just another question. I see a comment there. Really interesting flood drought infrastructure, Jonathan. So just some feedback. And the question is, will you be quantifying flood area duration and depth using RS and modelling and linking to impacts on the greenhouse gas emissions, especially in the natural flood management areas?
I think the first part, yes, we want to be quantifying flood area duration and depth. We will attempt to use remote sensing. I think there can be issues of, again, sort of temporal sampling and whether we have remote sensing retrievals at the right time to capture those flood inundations. We'll also have fixed infrastructure in the field that can be there for when a flood occurs, and that then records that information. We hope that you know, as we develop this over the next 4 years, the drone in a box and having unmanned or non-line of sight drone use could enable us again to have like a drone based out in the field, and it's triggered to do some sampling when required. And I think, yeah, the link then to impacts on greenhouse gas emissions, I think we're kind of in the sort of early days of thinking about that. I mean, if you're coming at that from the perspective of inundated land where you might have increased methane emissions, for example, I think that, well, it's something we think about in particular circumstances like the fenlands, but we don't really think about it much in terms of other wider floodplains. But I think this is becoming a sort of hot topic in Africa, where methane emissions are shown to increase with large areas of inundation.
Great, Jonathan, thank you. I know we're going to time here, but I just had a quick question, and you kind of answering it there, and that last response was just about drones and the work that you've done on the flood measurement. It seems that, you know, drones are becoming a great, I suppose, not a sensor so much, but a great vehicle to use sensors. Do you see a lot of use in the future on using drones to support your work and sensing, monitoring?
I think Basically, yes. I think sometimes it's actually taking that camera technology, as I say, and sort of maybe fixing that on to a bridge or other high point where we can have a sort of semi-permanent deployment of a camera. Because I mean, whilst drones are great, at the moment we still need someone to go out to the field to fly that drone, and that's expensive staff time, as well as meaning that we only get data when someone is out there in the field. So it's really moving towards those automated, for fully automated drone systems, if we can get sort of the CAA permissions to fly them.
Yeah. Great. Thanks, Jonathan. Just we'll keep the time there. So thanks everybody for the questions, and what we'll do after this for all speakers is we will share slides with those registered as well, and the video will be made available. Thanks, Jonathan, again. Very much enjoyed and great sharing of knowledge of those case studies. Thank you. Maybe Grace will say stop sharing. That's fantastic.
Yeah,
thanks.
sorry, thank you. Cheers.
Thanks. So we'll move on to our next speaker, and Dr. Aziman Khan. And Aziman, I'll ask you if you can start to share your slides. That'd be great. And just to give a bit of an introduction, Dr. Aziman Khan is an environmental data scientist at the Department of Geography, Geology and Environment at the Worth Institute of Environmental Futures at the University of Leicester. And she comes with extensive experience in geospatial analysis and machine learning. She's worked on critical challenges such as biodiversity conservation and carbon capture methodologies. She's currently part of the team working on the UKRI AI for Net Zero project. That's self-learning digital twins for sustainable land management, and works on geospatial AI-driven solutions for the modelling of greenhouse gases from lowland agriculture peatlands in the UK. So very, very timely and topical for giving us some case studies in digital twinning. And Aziman, delighted to have you here, and I'll hand over to you.
Thank you for the introduction, Jim. First of all, can you see my presentation?
I can indeed.
Full presentation mode?
Yes, can see it. Thank you.
Perfect. Thank you. So, hi everyone. Thanks for having me. And I will be talking about what digital twins are and how can they be used for informing land use decisions to achieve net zero. So let's start with what digital twins are. They are basically dynamic virtual replicas of a real-world system, whether it's a building, an ecosystem, or some aspect of the environment. What makes them unique is that they update in real time and are functionally identical to their physical counterparts. Now, in some cases, you'll see that they update in near real time instead of real time or even periodically. But it's the fact that they are connected to the real system through the feedback loop is why they're different than, let's say, 3D models or data assimilation. And this property of being functionally identical and being updated regularly is what makes them a really good decision tool. For example, if I wanted to test what happens in this image here, if I were to replace all these trees with buildings, I don't have to make those irreversible changes in the real system. I can test that approach in my digital twin. And because it's functionally identical, it will be able to inform me what's going to happen when I actually do that. So the idea is for them to be used as decision support tools. And one example I really like to give is Google Maps, which are essentially a digital twin of our transportation system. They help you make decisions on which is the fastest route to work, and they also update in real time so they can inform you if there's a traffic jam ahead. So let's talk about how they work. What's the architecture of a digital twin? So this is a very basic architecture of a digital twin. And of course, different digital twins can have different architectures, but these are some of the main components that you will find in a digital twin. So it starts with observations. Usually multiple sources are involved. We have drones, satellites, IoT sensors. And this is the regular flow of information that updates our digital twin. This is then connected to other data sources. Here we'll have static data sources or simulated data sources. Together they form this data library, which is then integrated. If you have a large amount of data, you'll rely on AI tools for this integration as well. And to derive insights from all this data, we use AI models. We can also use traditional models, but AI models would be faster and sometimes more accurate. Typically, you'll use more than one AI model, and each AI model will have its own functionality. So they could be modeling a specific aspect of the physical system we're trying to twin. And of course, when we have several data sources involved and several models involved, uncertainty is going to be a factor. So keeping a track of uncertainty and knowing how far your predictions are from reality is very important. So uncertainty quantification would also be a part of your digital twin. All this happens in the background, and these are connected to a very user-friendly visualization tools where all these insights can be presented in a way where it's available for a wider audience. And these visualization tools are designed in a way that they even people with all levels of expertise can interact with them easily. So how can we use digital twinning to inform land use decisions to reach net zero? The advantage of a digital twin over traditional modeling approaches for making land use decision is the ability to provide real-time monitoring and policy decision support. So firstly, it will provide you this integrated information, which can help you get a baseline of emissions coming from a particular land use, which is crucial for developing any policies. Then, because we can closely monitor how policies are affecting the emissions and how they are likely to affect the emissions in the future, we can adjust the policies dynamically using digital twins. Thirdly, they connect the technology to real-world applications, which promotes public and stakeholder engagement. So no matter how sophisticated your AI models are, if they can't be used by policymakers or your clients, then your technology is not really being used. And lastly, they allow you to test net zero strategies before implementation. So for example, if the government has a policy that planting X number of trees by 2050 is going to reduce emissions by Y%, digital twins can help you understand if those numbers are correct. Now, here are some examples from the UK and from around the world where digital twins are being used or can be used as a decision support tool for land use and net zero. So firstly, we have enhancing carbon sequestration and reducing emissions through land management, under which we have two AI for UK, AI for net zero UKRI projects. One focuses on forestry and reforestation, and the other one to optimize land use for food production while reducing emissions. This is the project I'm involved in, and I'll be talking about this in the later slides. Then we have maximizing land efficiency for renewable energy deployment. So you can use digital twins to select the sites where you want your solar farms or wind farms to be. Low carbon urban planning and smart cities is one of the most popular applications of digital twins. We have several examples from around the world. One would be Virtual Singapore, which is a digital twin of Singapore City, which simulates building energy consumption, traffic flow, and other environmental impacts. And then we have digital twins for climate resilience and disaster preparedness. This example is from Netherlands, so climate adaptation digital twin, which not only helps you make decisions regarding flood prevention, but also how to progress development while being carbon neutral. So to give you a more in-depth example of how digital twins can inform land use decisions, we have the AI for net zero project Self-Learning Digital Twins for Sustainable Land Management. It also includes ruminant farming, but I would be focusing on agricultural peatlands. This is being led by Professor Heiko Balzer at University of Leicester, and other university partners are also mentioned here. So basically, the lowland peatlands of East Anglia, which are highlighted here in this red circle, are very important for food production, but they are also a hotspot of CO2 emissions. So basically, what happens is the drainage practices required to make this land productive, or for you to be able to farm on them, it leads to increased oxidation, which then leads to soil carbon loss and CO2 emissions. So the goal of this project is to develop a digital twin that will allow stakeholders, which would be farmers, landowners, or policymakers, to identify and analyze opportunities to reduce greenhouse gas emissions in peatland farming. So what it does is it predicts CO2 emissions and crop yield based on integration of different AI models, which derive insights from climate data, land use management information, satellite remote sensing, climate projections, etc. It also has a self-learning feature, so it's not just the data that is being regularly updated, but the models also become more accurate over time as new data comes in. So just to show you what it looks like and how a user can interact with it, it starts with a very simple interface which highlights where the area is that we are focusing on. And as a user, you can zoom in into any of the fields within this area. This field boundary map from UKCH is used to select specific fields. You can also select more than one field, essentially a small area if you wanted to. And then you can go to the calculator option right here. When you click on this calculator option, it opens a dashboard. So this is what the dashboard looks like. And this is where all the options to simulate multiple scenarios are. So for example, right now in this version, there is option to see historical values for your field, and also to see, to predict what would happen with changing scenarios. So some of the scenarios would look like low emissions, global warming, less than 1 degree centigrade, or high emissions, etc. We also have a near real-time function, which will show you values based on the most recent data. Usually in our case, it comes from satellite, so it would be 14 days, but the weather data would be updated more regularly. And then we have options to select different crop types, so spring wheat, winter wheat, or maize. And years, I think in the past, it goes up to 2006, and in the future, this version had it till 2080. On the left side is where you see the results. So what it does is it shows you an annual graph of NEE. NEE is net ecosystem exchange, which is essentially the difference between the amount of CO2 that is being released and that is being absorbed. So when it is positive, that means you have emissions. When it's negative, that means you have absorption of CO2. And just below this, you get a summary of all the values. So you'll get an average NEE, annual NEE, and crop yield, which would be in tons per hectare. And the NEE here is being measured in grams of carbon per meter square per day. So the way we expect users to interact with this tool is they can look at their field's history and understand what the baseline emissions are based on the crop they are sowing. Secondly, they can also simulate the impact made by management choices. So they can choose to grow a different crop in their field and see what happens if they grew maize instead of winter wheat in a particular year. What they can also do is they can plan for and respond effectively to climate change events. For example, historically, if they had a year that was particularly dry or particularly wet, they can see how their crop yield or emissions were affected, which can help them prepare better next time that climate event happens. So this is a general idea of how how a user can interact with this tool. And the next few steps, I think, are to increase the catalog of crop types we offer. So we would like to see some vegetables in there, lettuce, leek, etc. And also functions like also being able to simulate sowing dates. So what happens if you were to move your sowing dates by a month or 15 days, 15 days, and the same with harvesting dates. I would also like to briefly mention the @Trees project, which is also a AI for net zero project, which is being led by Professor Daniel Williamson, University of Exeter, which focuses on initiatives to create new woodlands and forests. So here it gives you options on, so you get to select how much area you have for planting trees, what other ecosystem services you'd like it to affect, so how much carbon storage you want it to do, and it simulates scenarios. It gives you a planting strategy on where to plant, how much to plant, and also how associated ecosystem services would be affected. So yes, that's it from me. This is the basic description of what digital twins are and an example on how they're being used. And I would also like to give a shout out to the team that's involved in this project. We have a very large team. So feel free to ask any questions.
Thank you, Azima. Thanks very much for that talk, and good to get a definition of digital twinning. There's many, so it's good to see that in clarity and some examples. So what I can do now is open it up to anybody that has any questions. So again, if you have a question, please do raise your hand and you can ask it yourself, or if you want to post it in, can. And I just see there's one question posted there, so maybe I'll just start off with that. It's from Ian. Just, will the Fen peat digital twin be updated when the updated England peat map is released in April 2025? So that's a question came in.
Yeah, so definitely. If we obviously want to give the latest data, so whatever information on peat depth and extent we can find, we would like to update it in the digital twin.
Okay, great. Asma, thank you. Time for any other questions anybody has? Just maybe while people are thinking about questions, I was just going to ask a more general one, just because on digital twinning, and you know, how accurate are they? You know, have you any work done to show, you know, the kind of accuracy from what you estimate to? I'm not going into a technical question here. I'm trying to avoid that, but just a more general question. You know, is the evidence there to say that digital twinings are sufficiently accurate to allow you that if you are modelling and you estimate reductions, you can see close to that?
Right. So in our digital twin, the models are based on flux tower data. So obviously models are only as accurate as the data is. What we are seeing is that generally it works well for historical data. But again, we need more validation for future data sets. For example, if you're projecting, making a prediction for 2050, because there are a lot of uncertainties associated with downscale chestnut and chestcap data. So that is something we need to account for. But generally speaking, if you wanted to use it for monitoring how NEE emissions are changing and accounting on a yearly or seasonal basis what the change is, they can give you very good information.
Yeah. Great, thanks. And I suppose just to maybe follow up on that, is there any particular real-time data is most crucial for a digital twin? Does it very much depend on the model you're trying to build out?
Yeah, exactly. It depends on what you're trying to model. For in our case, it would be the weather conditions, and it would be the how the crop is growing, so the crop cycle. So in our case, it's remote sensing, and obviously we don't have a direct connection to flux tower data as of yet, but that would be obviously very useful. So we rely on weather data, near real-time weather data, and satellite information.
Great, thanks. And see, just in terms of, I see all the questions come there. Just I wanted just to ask them myself. See, in terms of working with policymakers, and you mentioned about having the tools. is there work done on engaging with those focus groups within stakeholders to find out what kind of interfaces they want to see or how they use the tool?
Yes, exactly. So we have a dedicated person working on policy side of things, and we have regular stakeholder meetings. We very much want their input, and we only want to add functions that they actually want to see. On top of that, we have a dedicated team which is working on the psychological aspects. So we are all looking at at the same thing from different directions. So how likely are farmers to adopt AI, and how do they feel about AI? So it's not just about creating a technology, but it's also about looking at the economical and social aspects.
Great, thank you. Just see that there's two other questions coming there. One of the questions is, can digital twins be utilized for early detection and monitoring of forest pests and diseases?
Yes, they can. So you'll have to add a component model that focuses on that. So each functionality should have an underlying model working on it or integrated models working on it, but it can definitely be done, especially with remote sensing. A lot of hyperspectral data is being used to identify pests and diseases.
Great. So hopefully that answers the question. I think it does. There's just another question there. How can process-based models like Roth-C be integrated into digital twin frameworks, and are they used as core simulation engines?
Okay, so we create something called emulator models or surrogate models, because Joules or these Earth system models are very heavy to run. We can't actually run them in the background of the digital twin. So we create AI-based lightweight models that try to replicate functionalities. So for something like Roth-C, we could look at a physics-informed model, which will incorporate the equations or the physics associated with that model, but we'll create a surrogate model um, that tries to replicate that functionality. In our twin, we're also using simulations from Joules data. So Joules, crop-specific Joule runs based on the crop types I mentioned are actually used to train a surrogate model that tries to replicate functionality of Joules crop without actually having to run it for days.
Great, thank you. And I think that does answer the question here, but if not, you can comment back on that. I'll just open up if there's any other further questions, some good questions there. I don't see anything else coming through. Final call? Nothing? Great. Thank you, Azima, again. Very much appreciate the presentation and the case studies. We'll move on to the next speaker now. Delighted again here, we've got Toby Wayne is going to give us a talk. And Toby, if you can start to share your slides, that'd be great. So Toby Wayne is a reader in applied remote sensing at Cranfield Environment Centre in Cranfield University. And Toby is an agriculture engineer, and his research focuses on future agroecological systems using remote sensing. He addresses challenges like image data integration, information robustness, and system optimizations for farmers, land managers, and policy practitioners globally. His extensive experience in illicit crop monitoring in Afghanistan led him to focus on food security and commodity markets, including tracking and mapping wheat changes in North America. He's also led commercial projects mapping cocoa, coffee, lettuce, tea, and sugar beet production in various countries internationally. And I suppose additionally, he's worked on water resource management using remote sensing, including for sustaining Himalaya water resource and a changing climate and emergency flood planning and management. So delighted, Toby, to have you here today. And I know you're giving your talk on geospatial technologies for monitoring land use changes. So delighted to be able to provide a talk on this, and again, another topical area within digital opportunities. So Toby, I'll hand over to you.
Thanks very much, Jim. Just to check, can everyone see my slide full screen?
Yes, can indeed.
Perfect. Okay, yeah, so thanks very much for inviting me to talk today. Yeah, so actually, there's a lot going on with remote sensing at the moment. So we've got lots of new sensors. I'm thinking about there's some projects looking at things like fluorescence from satellites. There's geostationary satellites. There's hyperspectral satellite programs that are all going to be launched in the next few years. And we're getting more and more sensors that we can use. Given the theme of the topic today, which is geospatial technologies for land use change, I'm probably going to talk less about the technologies, but more about the applications that have been using those technologies. Other themes that you might want to listen out for while we're going through the presentation are the use of AI for classification, remote sensing data fusion. I think actually the previous speaker talked a lot about digital twins, but there's a connection here about the data fusion. And decision-ready data as well. So those are kind of some themes that I'm trying to bring out. And then scale. So the great thing about remote sensing is that the different types of sensors can collect imagery at different scales. And that's been really, really useful for my career. I've now been working in this area for probably about 20 years now. And we can do everything. If we're looking at landscapes, we can look at everything from country level surveys. So in the example on the screen, we've got Côte d'Ivoire and Ghana, where we're looking at cocoa. Then if we're coming down to more the what's in what field scale, which is probably a lot of what we're thinking about in terms of land use change, is thinking about what actually at the field scale. We can do things like digital classifications. And then finally, if you're more of sort of a farmer or you're interested in maybe the in-field variation. So in this example, we can see some crop variation here, and we can manage those areas differently. And then as we go down into those higher and higher resolutions of satellite imagery to measure these scales, we've got different types of stakeholders who are interested in the information that can be derived from those. But there's some kind of common threads through here as well. So lots of people are interested in things like food security or taxation. So I think, understanding how it's been traditionally a very large area for thinking about crop monitoring. And as we move much more into thinking about net zero, it's much more about compliance and thinking about the environmental impact of what we're doing with our land use change. There's actually kind of still, even notwithstanding the scale, there's probably 3 questions that people ask, and this applies at sort of the country scale and at the field scale. So the first one really is, what's happening now? So if I'm a country, how much wheat have I got in growing in Indonesia? Or if I'm a farmer, how well is my wheat crop doing compared with my, how other areas? And the second one is exactly that, is how does what I'm doing compare with my neighbors? So if I'm Indonesia, I'm growing rice. Am I likely to have a problem with my rice crop? Do I need to think about buying rice in the futures? And then the final one is, what's going to happen in the future? So that could be 3 years, 5 years, 10 years. So what is going to happen with my landscape? The decisions I make, how is that going to impact the future? And this is actually going to affect all of these scales. So without trying to turn it into a lecture, because I didn't really want to do that today, I thought I'd put one lecture-y slide in. So the first question really is, what's possible with remote sensing? So the reason I put this slide in is remote sensing isn't a silver bullet. It isn't going to answer all your questions. The first thing I always say to the students really is, you've got to have an underlying physical relationship between whatever you're measuring on the ground and what you're detecting, what you're actually detecting with that sensor and the biophysical parameters of that crop. And we call that, this relates to what we call the spectral response of the image. We're also interested in the terms temporal and spatial. So temporal, we're looking at how things are changing through time. So we often can use things like vegetation indices, which are derived from remote sensing, to look at how crops are changing, the amount of green the crop is showing, and actually measuring those vegetation cycles. And then the final one is the spatial scale. So we're going to be looking at spatial scale in a bit more detail as we move through this presentation. And I think actually Jim mentioned it earlier. So everyone gets really hung up on exciting platforms, so drones and satellites, but it's actually really not that important what the platform is. It's actually what the sensor is that's important to us. So that's another thing to remember. So I thought, so I'm actually going to have, I've got two small cases and two slightly longer cases. And I'm going to take you on a short tour around Lincolnshire, then I'm going to jump to Vietnam, then to Afghanistan, and then back to the UK. So I thought I'd put this one. This is not strictly speaking land use change, but I thought it was interesting because it highlights the terms spectral, spatial, and temporal. So in this experiment, which we did using a drone a good few years ago now, probably about 2014, I think it was. We were working on a project with G's growers, and we were looking at whether we could use UAVs or drones to monitor crop disease. So you might think, well, why is that appropriate, or why is that important for us in the context of land use change? Well, disease is a factor when people are deciding what they might do in future land use decisions. So a good example might be because we're unable to use some of the chemicals for spraying oilseed rape, there's been very, very distinct changes in the patterns of growing oilseed rape in the UK because farmers are realizing it's not economical because of the disease pressure from the cabbage stem fly beetle. So monitoring disease is actually quite important. Now, what's interesting is it's easy, or so we probably know more about monitoring disease transformation or how it moves through the landscape than we do within the fields. So this project was really looking at, could we detect, if we used drones, could we detect the progression of disease? So if you look very carefully in the image, in the natural color image, it's not very easy to see the disease, but if we use infrared, we can actually see this disease patch area here. So this is detected and visible in the drone imagery. And then the disease is septoria, so it's causing this necrosis of the leaves, and we are seeing that in a reduction in the infrared part of the spectrum, which is resulting in this like dark kind of brown, sort of black dot. And the question is, it's an organic celery crop, so how much of the field do we need to destroy to stop it spreading? So if we can understand both the size of this patch and how it's spreading within the field, we can actually make a decision about that. Now, interestingly, we flew the drone the next week, and you can see the patch has got slightly bigger. And then this area here is actually where they'd attempted to destroy the crop. Unfortunately for the grower, they went down the wrong tram line. Fortunately for my experiment, they went down the right tram line because it allowed us to see how this is spread. So it's an interesting example of how disease progression. I've got quite a bit of research going on looking at that particular question. So can we understand better how disease spreads within fields? So that's my kind of like close up.
Yeah, well, it's watery.
So cute. Yeah.
I know, bless them.
If I move now to a completely different case study. So this is actually where we were looking for a commodity grower. We were asked to look at if we could provide information in Vietnam about their coffee production. So the challenge there was the coffee being grown. We obviously the grower, the people who are trading these commodities, they know what the production is, but they really wanted to know more about where it's coming from, and where the supply is, where it's actually been growing, and the extent of that. And on top of that as well, they wanted to know about what the age profile of the trees, the coffee trees, in order to sort of understand what their future will be of the supply. So we were brought in to basically to design a survey. So we've done lots of survey design over the years, and we decided to use a remote sensing approach to stratify the areas of interest, and then we sent out a team of 30 people on motorcycles to go and visit sites, sample sites, and they had to face quite difficult conditions, as you can see in here. But actually, this is a really good example of where you can use remote sensing to try to improve the design of your survey and integrate that into the ground survey design. And then we actually used a statistical approach to relate the imagery data, the classifications of the satellite imagery with the ground data in order to get more information about tree profiles. What's become more important perhaps than the production now is actually compliance with things like the European deforestation regulation. So actually that's a nice segue to my next slide. So on the theme of scale, I thought it would be interesting to have a look at this slide. So the challenge if you're growing commodity crops is that you now have to prove that you're compliant to the European deforestation regulation. The challenge we have is that the data sets that people are using, things like the Hansen Global Forest Loss Product, are at a scale which is not necessarily appropriate for the size of field boundaries. And this is, so I'm not really criticizing the product because it's a global product. So it's freely available to be used, but my comment really is about sometimes we need to think very carefully about the scale versus what we're trying to do with it. So within the actual deforestation regulation, it's a very long document if anyone's looked at it. There's a whole section on using the most appropriate method available. So what they're actually trying to do is drive companies using probably the Copernicus European satellites to build products to help to support this. So alongside that, we've also been doing work looking at whether we can use different types of satellite imagery. A lot of the commodity crops are grown in the tropics, which have very high cloud cover, which is not great for optical. So we've been doing a lot of work on looking at whether we can use SAR imagery or even sort of composites of high resolution optical. There's some relating to that. There's some interesting developments around data fusion for remote sensing. So we're seeing the first sort of sets of products where you can actually get a daily product, which you can basically have satellite imagery, which is collected on sort of several day intervals. And then the days in between are filled in using basically AI models. And so you effectively create synthetic data where there's cloud covering certain areas. Sounds like a great idea. Have a think whether you think that might have some flaws. So, yeah, so the first of my slightly longer case studies. Actually, this is probably the first time I've talked about opium poppy in a sort of more open forum. So I've been working on this topic probably since about 2004. And we were originally brought in by the UK government to look at the figures that were coming out from the United Nations and the US on the production of opium poppy. Illicit crops or illegal crops are kind of not in the headlines as much as they were perhaps back, maybe that's when we were doing this work originally. Obviously still really important because the supply of illegal drugs into the UK and the damage to society that those are causing is still really important. In terms of opium poppy specifically from Afghanistan, so I think it's still the case, probably even higher than 90% is being produced by Afghanistan, and it is going. Most of the UK supply is coming via that route. It's actually linked to funding terrorism. It's illegal to grow it in Afghanistan. So you might ask yourself, why do farmers grow it? Well, the reason is because the security in Afghanistan is very poor, and they're often forced to grow it. A good example might be in order to get credit to buy wheat seed, they're asked to grow some opium poppy in order to be able to do that contract. So it's a very challenging security. And in fact, if you're watching the sort of news at the moment, what's interesting in the last about 18 months to 2 years is that since the Taliban have taken back over in Afghanistan, they have actually banned the cultivation of opium poppy. So that has led to a reduction in the amount being produced. So the international community are watching really carefully about what's happening. And of course, that means we need to have methods for monitoring opium poppy. So just a little bit about how poppy is grown in Afghanistan. So as you might expect, it's quite high in terms of hand labour, often really unfortunately using child labour. There are some small tractors in Afghanistan, but mainly they use for sort of tillage operations. Things like hand weeding is commonly used. In terms of how opium poppy is harvested in Afghanistan, there's some photographs here. So what happens is there's a tool called a lancing tool, which is basically a piece of wood with razor blades. You can see if you look very carefully, you can see like 5 little lines. This razor blade is scored up the side of the opium capsule. Then the opium is left for overnight, and then it bubbles out. You can see the sap bubbling through the wall of the opium, the capsule. And you can see there's multiple lines. So this is done over several days. Then someone comes along with this tool here called this like kind of basically this lancing scraping tool, and then they gather it all up, and it's a big. You end up forming a sort of brick of opium poppy. The advantages, of course, of that is if once you've got that, you can hide it under your mattress and then sell it on a later date. If you were thinking about the same area that you were growing wheat with, you'd have to have probably several trailers of wheat for the same area. So it's a much more compact product at the end of the day.
There we are.
So the challenges, of course, if you're trying to do a survey in Afghanistan, are the security issues. So in the example here, we actually were working with the United Nations. They had people on the ground going out doing surveys for this international survey. And the real tragedy was that people were driving over improvised explosive devices and getting blown up. You can imagine if you're going into an area that's got very poor security, if you're going in and maybe asking farmers about how much of this illegal crop they're growing, you don't get a very good welcome. And it's even worse than that. In some sense, basically, if you walk into a field holding a GPS, you're likely to be shot. So we really wanted to look at methods. In fact, we basically shifted from doing ground data into using high resolution satellite imagery instead, which obviously has the advantage of being able to do that remotely. However, we did have some ground data to kind of validate and to calibrate what we're doing in our imagery. This tractor in the image here is actually doing some eradication of poppy. So that at the time we were doing this, there was a big international push from both the governments of Afghanistan and the US to eradicate poppy. So we were also looking at using remote sensing to monitor that. So how do we calculate the poppy area? Very simple equation, which is we need to work out the average proportion of poppy in a unit area, and we need to work out the total active agricultural area. So if we have the average proportion times that by the active agricultural area, we can have an estimate. And that's actually how we do it. So actually, there's a lot of information on this slide. So let's go through it carefully. So what we have here is the sample design for the Helmand province in Afghanistan. So Helmand is about the same sort of height as England, or sorry, yeah, probably England actually, if the actual in terms of the distance across here. It's one of the key areas where opium poppy's been growing. It's usually around 100,000 hectares of opium poppy. Currently, I think that's dropped right back to virtually zero. It's a river-fed system with irrigation supplementing the main river channel. So the approach is very much a data fusion approach. So we had a combination of background mapping from medium resolution sensor. In this case, we used a satellite called UK DMC, which is 30-meter or 22-meter resolution. And we then took that information and we stratified that based on the spectral properties. And then we had the samples. If you look really carefully, you can see these little red dots. You probably can't see them very well on on the Teams link, but you can see the orange squares. So the orange squares are the footprints of Iconos images. So those are 10 by 10 squares. And then within each of these 10 by 10 Iconos images, we have these interpretation squares. So this is where, at this time, we were using manual photo interpretation. So the interpreters, I had a team of interpreters doing this because we were doing it for every province, who were drawing around these polygons manually and labeling them as poppy and cereal and other. And we repeated that for all the samples. Luckily, poppy is very distinctive from wheat. You can just about see the difference in the corner here. If you look at the sort of this lighter bluey green color, that's opium poppy, and then the darker color is the wheat fields. So you can interpret it, fortunately. And then we do a statistical mapping between all of these samples and the satellite imagery, this stratified layer, and that allows us to work out actually the probability of poppy occurring in every pixel in the medium resolution image. So we have a map which is basically 20-meter pixels and the proportion, if you like, the distribution of the proportion of poppy. So let's have a look in the next couple of slides about how that was changing through time. So we actually started doing these maps probably back in about 2005 was the first one of the distribution maps. And then the key bit of the project we were working was we were looking at the influence of policy on how much opium poppy was grown. So basically the sort of darker, these purpley areas are where you've got very high levels of cultivation. And then as you go into the sort of reds and then oranges and then greens into the yellows and greens, you're getting lower proportion of poppy. So anything that's purple is very high, more than 40%. And we can see there's a lot of poppy growing here that if you went out in the field to any of these locations where you can see 40%, you would actually find poppy, in every other field effectively. And we can make estimates by adding up all the proportions in this area. We can estimate the total production. And then we can also cut up these areas into districts and then sum the proportions for every district and make district estimates. But in this particular map, you can see the progression. So it's pretty, there's loads of poppy growing here. As we move into 2008, still lots of poppy. And then in 2009, we see something quite dramatic happening. So we can, hopefully you can all see this red area here. So this central area is what was known as the Hellman Food Zone. So in 2009, there was a US policy which was to distribute free wheat seed to farmers in Afghanistan, in Helmand, specifically Helmand. And the idea was to try to displace opium poppy by flooding the market with free wheat seed. So we can see this change. And in fact, if we flip it the other way and do a map of distribution of cereal crops, it's very dramatically, you can see how much more cereal there is. Having said that, if you look more carefully in here, it's a little bit more difficult to see perhaps here. If I go back into the poppy one, perhaps, there are purpler areas spreading up higher into the valleys, and there's also an expansion of agricultural area. So if you actually look in more detail at these areas, and here's a really good example of something interesting happening with the limits of the Hellman Food Zone area. So the Hellman Food Zone area is defined with this dotted line, and it was set along this canal system. So you might be thinking, why would a canal stop the wheat seed going to the other side? Well, it's actually all to do with these locations here, where you've got the pathways through from the sort of main area into these more extensive areas. And what actually is happening here is that because the security is so poor, there is no movement of people or goods through this gateway here. In fact, it's actually really kind of shocking in a sense. People were growing vegetables out here, and there's people who are very short of food in here on this in the main area, and the vegetable trucks were queuing up here and they weren't allowed to cross, and then the vegetables were just rotting on the trailers. So that gives you a sense of how difficult things were moving through that area. But the map does show that there is a difference in the cultivation. So there was more wheat in this area to the south of the canal versus the north. And you can see this reflected in the high resolution imagery and also in the poppy distribution maps. So the sort of purple being the cereal in this case. And then in this, it's the poppy in this case. So we were brought in. The reason we were doing this was we were asked by the UK government to give an appraisal of how well this Helmand food zone was working. So we actually made this very simple graph to try and explain the difference. So we looked at the change in food in the poppy and cereal crops in the Helmand food zone between 2008 and 2009. So this is actually a change graph, and it shows that in the Helmand food zone, we did see an increase in cereal production, as you might expect when you distribute lots of wheat seed. But we did also see quite a lot outside the Helmand food zone. We did see a reduction in opium poppy in the food zone, but we saw an increase outside. And this is actually the bullet points we presented. So we presented these three conclusions, which were we saw large percentage increases in cereal cultivation, similar inside and outside, which is these two. And then we saw an 8% increase outside, which is that bit. And then we saw a 37% decrease. And you can probably guess which one of those figures was quoted by the PM, clearly the 37%. So yeah, hopefully you found that interesting. So my last case study is actually back to the UK. So I think I saw David Alexander from Peak District Park on the call today. So hopefully I don't say anything wrong here. So we've been working with Peak District for a few years now, and my colleague Dan Sims has been leading this work, and I'm presenting some of it on his behalf today. So we're really interested in whether or not we can use new technologies such as AI to improve the mapping of land cover and habitats. And often these are quite complex environments with different patches and different matrices of different types of habitats in kind of complex environment. So there are products out there, and again, this is not a criticism of those products, but it's like maybe 10 metapixel from the land cover map from CEH, for example, and then some other examples there. So with the work that Dan's been doing with Peak District and Turing, they actually looked at, and actually this came out of actually from some of the work that Dan had been doing on the opium poppies, where I mentioned earlier that we manually interpreted all of those squares. Well, actually, Dan had done some work on automating using AI, the approach of training a classifier using those same squares, and actually train that for Afghanistan. We then did the same thing, or Dan did the same thing, and actually they were able to produce this Peak District land cover map for 2023. I'll show some examples in the next slide. So this is really, really important actually, because Cranfield had originally been involved with the monitoring landscape change in the national park in the kind of 1980s, and that project actually that project was instigated because back in about nearly 50 or just over 50 years, when we joined the European Community, we also joined into the CAP, Common Agricultural Policy. So the original landscape change in the National Parks project was really to look at whether between 1970, just before we joined, and then 1980, whether the CAP was having any real different, an impact on the national parks. So that was why that work was commissioned originally, and it was a really cool bit of work. It used manual photo interpretation of aerial photography And really that has been the kind of key baseline imagery that's been used. That product, sorry, the baseline mapping has been used since like the sort of 1990s, really. And so what's exciting now is this new 2023 product has really enabled us to update that and bring that up into up to date. And the way we've done it is to use AI and aerial digital photography. So the project that Dan was working on with Turing Institute and David as well in the past was looking at what it did was it took the original polygons that were digitized from the manual interpretation and used those as training. So lots of people have probably used AI on the call today or know a little bit about it, but one of the key challenges is always getting enough training data to train your classifier. So we were fortunate in a way, we had lots of polygons ready to use. It's not without its challenges because of when interpreters draw round features, they can generalize, so that you have to make sure you've got consistency in the way the interpretations have been done. But the good news was with this project, we were able to very successfully, so with going through several loops of different types of training approaches, we got the accuracy into the sort of 90s, which is everyone likes to have 90% accuracy. And you can see here that there's in these little chips here, you've got some really nice examples. And this is now a product which you can actually look at and download. So I'll show an example of what it looks like in more high resolution. So if for those of you who are good at photo interpretation, you probably recognize that's Lady Bower Reservoir, perhaps. So we can see here, nice, interesting landscape with like sort of some shrubland moorland over here, some trees and some grassland areas. And when we map it across, we can really see how that new product is doing an excellent job of fitting the boundaries to those. If I flick between them, you can really see how that's working. So the great thing about these new products is now we have up-to-date, better accuracy and better spatial and thematic resolution that we can now use with existing data, and we can now see what the current changes are like, and they're at a scale that's appropriate and can match to the original data. So that's a massive transformation. To give you a sense of what the benefits might be, so I thought it would be interesting just to look at one small area. Again, this is not a criticism of the land cover map, because the land cover map is done at a different scale, and that its mapping accuracy is appropriate for its scale. But it does show quite clearly about the differences in the way these using satellite data versus high resolution data can affect the generalization of the data. So a good example might be if you were calculating from the pure area of these, you actually have a larger area because of the higher spatial detail. So you could end up, if you were feeding the high resolution data into sort of ecosystem function tools, you might have a completely different number. So, and it's an interesting dilemma that we all have to kind of deal with. Just one little blatant plug. With myself, Daniel, and Peak District National Park, and as part of Centre, have got a funded PhD, which is about to close. So if anyone knows anyone who is thinking about, would like to do a PhD looking at landscape change using AI approaches, that's about to close next week. So just Google kind of those terms or contact me directly afterwards, and then I can put you in contact. So just wrapping up. So hopefully, oh yeah, you might actually put it in the post. Yeah, so this is really kind of the last slide. So I'm interested in whether we can do things slightly different in our landscape. And also the question that I kind of like asking myself is, do we actually understand what is the optimum scale to manage plants? So typically at the moment we manage crops at field scale because it's a very practical unit. And then with precision farming technology, we can maybe go down to subsections of the field, sections of the boom width or then subsections of that in a precision farming sense. But actually, if we had, because we have so much more technology, could we start managing groups of plants or individual plants or even parts of a plant? And that's really, but do we need to do it? Is that optimum? Is it actually optimum to go down to that level? I think it's an interesting question, which from the research perspective is quite cool. And then to help us do that, we've invested in facilities, which some of you may have seen before. So if you're interested in finding out more, please give us a shout. And this is our phenotyping gantry, which actually is a bit like the previous slide. It has a robotic gantry with sensors on here. And then we can do things like look at one of the projects we had running a few years ago now was could we demonstrate the benefits of cover crops? So cover crops have been a really big thing in terms of land use change and protecting soil, but actually we wanted to quantify what the improvements were. So we could use this facility with control, because it's a glass house, to actually monitor those types of approaches. Yeah, so thanks very much. And if you have any questions, please let me know.
Thank you, Toby. A very interesting talk. And I have to apologise, my fire alarm went off in my building 10 minutes into your talk, and I had to leave, so if that's part of it, apologies. So we'll open it up to any questions from any of the attendees. If you have any questions, just post them in there, or if you want to raise your hand, I'll let you ask them. And just so maybe people are thinking about questions there, I was just going to ask, what do you think are the most significant land use changes currently being monitored or observed with geospatial monitoring? What's your thoughts on that? What's the most? I know you give some examples there, but
that's a really interesting question. I mean, I think a lot of the changes we're seeing, the thing that always surprises me is how quickly, if we're taking the UK as an example, if we're looking at arable systems, how quickly farmers will change what they're doing in response to a combination of the economics and also policy. So a good example might be, there's the latest environmental stewardship and those programs. Farmers have already responded really quickly to those programs and are actually engaging with those really quickly, and it happens over a relatively short period. So it shows that if we want to change what our landscapes look like, we can influence that through policy or economics as well. So in the case of the oilseed rape levels going down, and it's driven by the economics of those crops changing. I've done a lot of work on sugar beet recently, looking at disease progression in sugar beet, and sugar beet is another crop which is under great pressure from aphids actually spreading a virus. And it's quite a contentious area because of there's actually a derogation on using seed treatments to try to prevent the spread of the aphids. But it really, with scientific evidence to try to help make that decision, you can at some level decide what the economics of the crop is versus the environmental. So yeah.
Oh, great, Toby. Thanks for that. I was just going to ask another quick one. Just as we're talking about geospatial technologies, do you see how they might evolve over the next, say, 10 years to maybe help land use change monitoring? Is there anything you think or do you see anything coming down the road that will help?
Yeah, I mean, I think with the previous speaker, was talking about digital twins and Asmia. Really, I think that is it's an interesting area, which is, it's definitely a growth area. Remote sensing really feeds into that as well. The other area that we've been doing a lot of work on is really, it's going to sound really kind of technical here, but if you think, we've been doing a lot of work on looking at things like emerging properties. So what I mean by that is, could we make measurements with remote sensing that allow us to understand more about the sort of state or condition of the system? So a good example, so an analogy would be if a cardiologist looked at the rhythm of your heartbeat, they can tell something about how your heart is performing. So there's been some work already on looking at the vegetation profiles. So we've been doing a lot of work looking at the signals within those vegetation profiles in order to see whether there's any indication of like, is a system slowing down or is it tending to a position where it might change into a different state? So it's quite high level thinking, but what's really interesting about that is that we've got to make some really tough decisions about the systems we're working with. So if we had some tools which allowed us to understand whether a system is adaptable to, like, let's say, climate change or not, we can kind of triage the landscape to make the interventions. So some areas might be at a position where they're going to change into another state, and other areas we might want to keep them in the same state. And then there's another question is like, in national parks are really interesting. So if we're trying to keep the national parks exactly the same as they are, does that actually make them more vulnerable to climate change? Or should we actually allow them to change a bit more naturally in order to make them more resilient?
No, that's an interesting closing point there, yeah, to allow them to evolve a bit more rather than contain them. No, that's an interesting point. I don't think you and I can answer that one today, anyways.
Yeah.
But no, great, Jonathan. Or sorry, Toby, thanks. I was going to say, I've just got a comment come in here from Enda. Toby, when monitoring celery, you mentioned the farmer taking action that helped your research. How do you feel about introducing digital twins, and how much work is involved in this to help take preventive actions using real-time data?
Yeah, so I mean, for me, I mean, I've worked on model data fusion for many years, and digital twins for me is basically it's the logical next step in terms of like using a model. So we've already kind of tried to do some of that ourselves, as you might imagine. So a good example might be we've done a lot of work on, let's say, wheat modeling, using really off-the-shelf models, and we're looking at whether we can use them. We basically predict where we think we might be with yield, and then we use the remote sensing to actually nudge the model, and then you can then take a new trajectory of that model. So that, in a sense, is actually a digital twin. So I think this is going to be much more of a thing going forward in terms of like farm services are going to really want to try to use some of these modeling tools. And I think this kind of digital twinning approach is a way that allows them to do that.
Yeah, no, I think that's a good point. There is a, I suppose, not to say a partnership, but there's definitely close integrations with geospatial technologies and digital twinning to get, I suppose, better insights, for sure. I'll open up there. Any other further questions, just, or any comments? Nothing else coming through there? No? Okay. Listen, just thanks, Toby, again for your presentation, case studies. Very much appreciated. That brings us to maybe a closing. I suppose just some final remarks. I want to thank our three speakers again, Jonathan Evans, Aziman Khan, and Toby Wayne. Really appreciate you taking your time today to share these insights and case studies, and fascinating the variety of work that's going on and the use of digital technologies. And that was what today is about, is trying to give examples of that. So thank you all for that. I'm just going to say that we're going to share the recorded video with all registered attendees. So anybody that was here or couldn't make it, any of your colleagues, we will get that out as well. I'm just going to follow up as well, post this probably just a quick wee survey. So if you see it coming out, be delighted if you would give us some feedback, because our intentions here to run future webinars to follow up on this. And one of the ones that we're looking at running next, just due to some feedback, is on generative AI and how we can use that, but more of an explanation of how to use Gen AI rather than getting case studies. So that's something we'll be undertaking soon as well. So hopefully I'll share it with you. Listen, just to thank everybody for attending today. I want to thank Erica as well for supporting Lunds Hub. Very much appreciated today for facilitating this. I'll leave it at that and just thanks everybody, and hopefully have a good evening and a weekend. Thank you.
Thanks, Jim.
Bye.
Thank you.
Cheers,
Bye.
everyone. Bye.